Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be going over limiting reactants, and I'm going to go over a second problem. But first, again, I want to preface the problem by kind of going over what a limiting reactant is before we start on the problem. So just to kind of summarize a little bit, a limiting reactant is a reactant that limits the reaction or limits how much product you form. How does it do that? It does that by running out first. So my example, and there's a lot of examples using food, but for me, peanut butter and jelly sandwiches work. So in order to make peanut butter and jelly sandwiches, I need bread, I need peanut butter, and I need jelly. So if I have a jar of jelly, jar of peanut butter, and some bread, I'm going to make peanut butter jelly sandwiches for my group of people until I run out of whatever ingredients I run out of. Now, it's possible I can run out of all the ingredients at the same time and not have anything left over. But a lot of times you always run out of one ingredient before you run out of the other two. And so in this case, maybe I'm making my peanut butter and jelly sandwiches and I run out of bread. So as soon as I run out of bread, I can't make any sandwiches, even though I have peanut butter and jelly left over. Because the whole point of peanut butter and jelly sandwiches is to have bread with the peanut butter and jelly, right? So in that case, because the bread ran out first, it limits the amount of sandwiches I can make. I stop making sandwiches when I run out of bread, or I could run out of jelly, for example. So in the process of making my peanut butter and jelly sandwiches, if I run out of jelly first, then the jelly would be limiting the amount of sandwiches I can make, and therefore it would be the limiting reagent. And the other two, the peanut butter and the bread, would be the reagent that's in excess. I have leftover of those ingredients, right? So the same thing applies to reactions. So whichever reactant runs out first, that's going to stop the amount of product that I can form. Therefore, it limits the amount of product formed. And so a dead giveaway for a limiting reagent problem is when they give you different amounts of your reactants and they don't say anything else. They don't tell you, hey, this reaction reacts to completion, or this reactant reacts completely with this amount of reactant, right? They don't say any of that. They just say, hey, you have this amount of reactant, you have this amount of reactant of this other one, and so how much product is formed, right? So in that case, that's a dead giveaway that you've got a limiting reactant problem. And so you got to figure out which of your reactants is the limiting reactant. Okay, hold on a second. Okay, let's get started on the problem. So here we have our balanced equation, and we're asked how many megagrams of UO2F2, this is one of our products, can be formed from the reaction of 24.543 megagrams. That is not magnesium, that is megagrams. So 24.543 megagrams of UF6, which is one reactant, with 8.0 megagrams of H2O, which is the other reactant. So here they're giving me two different amounts of both of my reactants, and they're saying how much is formed. That's a dead giveaway that we have a limiting reaction problem, because they don't say anything about it reacts to completion, or this amount reacts completely with that amount. They don't say anything like that. So we have to determine which of these is the limiting reagent, or if there's any at all. Okay, so again, there's two ways of finding the limiting reagent. The first way is to compare the reactants. Compare the ratio of the reactants with the ratio in the formula, the mole ratio. So what you can do is convert both. If you're given masses of your two reactants, you can convert both of those reactants to molar amounts, like moles. So how many moles of each reactant do you have? And then compare that to each other with the ratio. Is it a 1-to-2 ratio or not? Or you could also take one of the moles of the reactants and convert it to the molar amount of the other, right? So if I have a certain moles of UFC, or I'm sorry, UF6, UFC, MMA. Okay, no. So UF6, I can convert that and find out, well, how much water would I need to completely react with this amount or whatever amount of the UF6 that I'm given. If the amount of water I need is greater than the amount of water that I'm given here, right? Then I don't have enough water. If it's less than the amount of water I give, then I have more than enough water, right? So you can compare the amounts of reactants and figure it out that way. The second way that you could do this is by figuring out which reactant is going to produce the lesser amount of product. Because the reactant that produces the lesser amount of product is the one that limits the amount of product that can be formed. So therefore, it is the limiting reactant. It's the one that's going to disappear first. We're going to run out of that one first, and the other reactant is going to be the one in excess. So we're going to do it that way since that's more straightforward. Also, they're asking us to calculate the grams or the mass anyway, so might as well just convert to the mass and see which one gives us the lesser amount, and then we're done with the problem. So here we go. So let's take the 24.543 megagrams of UF6. So here I'm going to start 24.543 megagrams of UF6 over 1. And now I'm going to start converting to my product, which is going to be the UO2F2. So what I need to do here is first follow the roadmap. Remember, whenever you're converting from one substance to another substance, you have to convert to moles. So that way you can use your mole ratio. That is going to be important. That's the first thing you should always be thinking is, I got to get to moles. I've got to get to moles. Why? So you could use the mole ratio in your balanced equation to convert from moles of one thing to moles of the other thing. Okay, so let's see here. So first I got megagrams. I got to convert that to grams. So that way when I get to grams, I can use the molar mass to convert to moles. So convert megagrams to grams. I know that mega is 10 to the 6 or 1 million. So I know a megagram is 1 million grams. So I'm going to put 1 megagram of UF6 on the bottom and 10 to the 6 grams of UF6 on top. So megagrams of UF6 cancel out. Now I have grams of UF6 on the top. Now I can use my molar mass to convert to moles. So I'm going to go ahead and set up that. So I calculated the molar mass of UF6 to be 352.03. So I'm going to have 352.03 grams of UF6 on the bottom to cancel out grams on top. And I'm going to have 1 mole of UF6 on top. So grams of this substance cancels out. Now I have moles. So now I can do the mole ratio. I can use the mole ratio in my equation. So I can use the coefficients. So 1 UF6 related to 1 UO2F6. So it's 1-to-1 ratio here. So I do that ratio. So that's going to be my conversion factor. So I have 1 mole of UF6 on the bottom and 1 mole of the UO2F2 on top. UO2F2. Okay, so now moles of UF6 cancel out. Now I have moles of the other substance. So now at this point, it's converting back to the mass. So in this case, since they're giving us megagrams, we're going to convert back to megagrams. So here I have moles. I need to convert back to mass. So I'm going to have to use the molar mass of this substance here. So the molar mass of this substance needs to be calculated. And that's 308.0288. Here's my marker. Oh, there it is. So here we go. So I have moles of UO2F2 on the top. So I'm going to put 1 mole of UO2F2 on the bottom. And again, it's going to be 308.0288. 308.0, what was it? 0288. 288 grams of the same substance. So UO2F2. This is going to cancel out. So moles of this substance cancel out. Now I have grams, and I want to convert that back to megagrams. So I'm going to use this ratio here, this relationship, but I'm going to flip it. 1 megagram is 10 to the 6 or 1 million grams. And so I'm going to continue down here. So multiply by that conversion factor. So I have grams on top. I'm going to put the grams on the bottom. So 10 to the 6 grams of UO2F2 on the bottom and 1 megagram of UO2F2 on the top. So grams cancels out with grams. And now I have megagrams. So at this point, it's all about calculating. I can calculate, multiply by everything on top. So multiply by everything on top, and then divide by everything on the bottom, and you get your answer, which is, and that is 2147.53. So 21.4753 megagrams of the UO2F3. Oops, F2, sorry. F2. Okay, so that is the amount of megagrams of the UO2F2 that is produced possible from this amount. So this is assuming that all of this reacts. If it does all react, then this is the amount in megagrams of the product. So now we have to do the same thing for the water. So we're going to do the exact same calculations, except for, of course, the molar mass of water. So here we got 8 megagrams of water. So we're going to put 8.0 megagrams of H2O. And we're going to put that over 1. And so again, the first step is to convert megagrams to grams. So we're going to use this conversion factor again. So we're going to put 1 megagram of H2O on the bottom, 10 to the 6 or 1 million grams of H2O on top. So megagrams cancels out. Now that I have grams, I'm going to convert to moles using the molar mass of water. So the grams of water goes on the bottom. The molar mass is going to 18.0154. So 18.0154 grams of H2O. And on the top, it's going to be 1 mole of H2O. So now I can cancel out grams. Now I have moles of water. So now I can use the mole ratio in my balanced equation. So moles of water to moles of the UO2F2. So it's 2 to 1. So I'm going to use that. So moles of water is on top. I'm going to put moles of water on the bottom. So it's going to be 2 moles of water. And then on top we have 1 mole of the UO2F2. So again, moles of water cancel out. And now I have moles of my UO2F2. So again, same steps. I'm going to convert. I got to get to megagrams, which is mass. So I'm going to use the molar mass to convert to mass in grams first, and then use the relationship between megagrams and grams to convert to megagrams. So first molar mass. So here, these last two steps are exact same steps here. So this one and this one. So I'm going to use this one here. So 308.0288 grams of UO2F2. And on the bottom is going to be 1 mole of UO2F2. So the moles of this substance cancel out. Now I have grams, and now I can use the same conversion factor or the same relationship to convert grams to kilogram or megagrams. So I have grams on the top. So I'm going to have 10 to the 6 grams of the UO2F2. On the bottom, I'm going to have 1 megagram of the UO2F2 on top. So the grams of this substance cancel out. Now I'm left with megagrams, which is what I want. So at this point, I can multiply across the top, divide by everything on the bottom, and get my answer. And when we do that, we get 68.3923. So I'll write that down here. So 68 point, what did I say? 3923. 29, oops, what did I say? 3923. So 3923 megagrams of the UO2F2. So now when we look at the amount of our product being formed by both reactants, we can see that this reactant here, the UF6, produces less than that from the water. So this amount of water, if it reacts completely, would produce this amount. The amount of the UF6 that we're given, if that were to react completely, would only produce this amount. So that means that the amount of UF6 we're given is going to run out first. It's not going to produce as much. So this will run out first before this. So the UF6 is our limiting reactant, so it's going to limit the amount that we can make. So the maximum amount we can make with these amounts of reactants is going to be the 21.4753 megagrams of the UO2F2. Now, before we finish, let's talk about significant figures. For those of you who are interested in figuring out sig figs of your answer, remember the number of sig figs in your answer has to be equal to the smallest number of sig figs in your measurements, right? So it should be equal to the measurement with the least number of sig figs. So remember, we can ignore the exact numbers. So any metric to metric, where it's metric mass to metric mass, that's going to be That's going to be exact, so we can ignore it. So 1 megagram to a million grams, that's exact. We can ignore that. So this one we can ignore as well, the 1 megagram to 10 to the 6 grams. Mole ratios we can ignore because that's a counting number. So 1 to 2, 1 to 1, that's going to be exact. So the molar masses and the mass we're given are really the main ones. So the molar mass here, this has 7 sig figs, and this molar mass has 5. And then here is the measurement that we're given in the problem. So that's 5. So the least number is 5. So our answer should have no more than 5 sig figs. So we got 1, 2, 3, 4, 5. So we're going to cut it off after the 3. Since this is a 3, we don't round the 5. So the final answer would be 21.475 megagrams of the UO2F2. So that is our amount. So that's the maximum amount that can be produced from these amounts of reactants. So I hope this was helpful. If it was, if you enjoyed this video, if you learned anything from this video, then please by all means like the video, hit that like button, share the video with your friends, subscribe to my channel, and when you do, make sure you click that notification bell and click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem you want me to go over, or a question you want me to help you answer, or if you have a topic you want me to cover or talk about in a future video, I would love to do that for you. Thanks for joining me and have a great day.